Okay, so let's go ahead and enable MPLS on the rest of the devices. So on XR2, router 2, XR3, and router 3. And from their point of view, let's say that we're just going to enable this under their global IGP processes. So on router 2 and router 3, we're simply going to go to our routing process. If we show run section router, in this case, we're running router ISIS1. So under router ISIS1, we'll say MPLS LDP autoconfig. Same thing on router 2, router ISIS1, MPLS LDP autoconfig. Okay, the end result of this, when we look at the show MPLS interfaces, should tell us that on every interface that we were running IGP, we're now also running MPLS labeling. And specifically the label protocol that we're using should be LDP, Label Distribution Protocol. So from router 3, if we look at the show MPLS interfaces, it says this is on interface gig 123, 312, and 313. When we look at the show CLNS interfaces, this should match up on a one-by-one basis where every interface is up in terms of CLNS, or in terms of ISIS routing. So if we look at the show CLNS interfaces, pipe include line protocol, we see that there are 1, 2, well, actually, let's say, pipe include protocol or routing protocol. Okay, this means that we have ISIS enabled on 3 links, gig 1.23, gig 1.312, gig 1.313. When we look at show MPLS interfaces, this should be on a one-to-one basis because we're enabling this globally under the IGP process, so any interfaces that are running IGP are also going to be automatically running LDP. So if you were to have a choice in terms of how are you going to configure LDP, this is going to be the simple way to do it. That we'll see that this is also a protection mechanism that if for some reason you enable IGP on a new interface and LDP is not enabled, that's when we can have a traffic black hole in the core. But in this case, since we're running LDP autoconfig, as soon as we enable ISIS on the new link, it means that LDP is automatically going to be turned on as well. So same thing is true with iOS XR. On XR2, if we look at the show run router, or show run router ISIS, we're going to go under ISIS1 under address family IPv4 unicast and say that MPLS LDP is enabled with autoconfig. And same thing on XR3. So router ISIS1, address family IPv4 unicast, and MPLS LDP autoconfig. Okay, just like in regular iOS, if we now look at the show MPLS interfaces, it should show us here that and actually what I did not do was, let's say, show run on XR. Even though I enabled LDP under the process, you still have to enable it globally. So in iOS XR, regardless of whether you're doing BGP labeling, traffic engineering labeling, LDP labeling, you always have to go to global config and say MPLS LDP. Okay, that's just turning the global MPLS process on. So same thing here, MPLS LDP and then commit. Okay, if we now look at the show MPLS interfaces, we can see now it's enabled. So previously, even though I had the autoconfig command, it does not give you a parser error when you go to commit this if you don't have MPLS enabled globally. But we can see from this output, when I said show MPLS interfaces, it didn't show anything. This means that the process is not on. Okay, now it says that LDP is enabled, but tunneling is off and static is off. This output you'll see is similar to regular iOS when we look at the show MPLS interfaces that says, are you doing labeling with IP, or in other words, with LDP, versus tunneling labeling, which means MPLS traffic engineering tunnels, BGP labeling, which is going to mean IPv4 unicast BGP, or static labels, which is basically the same thing as like a static route. But in the vast majority of cases within the MPLS core, since we're already running IGP here, and in our case our IGP is IS to IS, we would also want to run LDP on every interface that we're running ISIS. Now in our current case between router 1 and XR1, we only have LDP enabled on this direct connect link between them. We haven't enabled it on these diagonal links or these east-west links to the other routers. So we'll see that when we actually go to forward packets, we will have a problem using the MPLS labels because LDP is not enabled on every single interface. So what I mean by this is that if we were to go to router 2 and look at the show MPLS forwarding table, notice that there's some outputs that say no label here. These are the ones that are pointing out gig 1.12, which is where we do not have an LDP adjacency over to router 1. So more specifically, if we show into this forwarding table, pipe include GI 1.12, we can see all of those interfaces have no outgoing label. So in terms of troubleshooting problems with LDP, this is going to be one of the most basic ones. If you don't have it enabled on the interface, you can't form an adjacency, you can't do any of the label bindings, and then ultimately you cannot do MPLS forwarding. So within the scope of the lab exam, for the troubleshooting section, if you were to say, maybe the problem is router 6 cannot ping router 10, and these are supposed to be layer 3 VPN customer edge routers of the MPLS network, even though we might have our control plane established, like we have BGP routing from router 10 to router 2, maybe we have VPN v4 routing that's going between router 4 and router 2, we have maybe OSPF routing here, we'll see that there are cases where the routing control plane can be working, but the MPLS control plane is broken, and the end result is that traffic would be dropped, traffic would be black holed in the MPLS core. So we'll see just because you have the route installed in the table doesn't mean you'll actually be able to reach it. And this is one of the most common problems, that if LDP is broken, then everything else on top of it is going to be broken. Okay, so in our case here, let's assume that we don't have that problem. We're just going to enable MPLS on those other interfaces. So from router 1, we'll see on gig 1.112 MPLS IP. On gig 1.12 MPLS IP. And we should see almost immediately that we get this log message about the LDP neighbors. As I had mentioned before, in the case of iOS XR, these logs are disabled by default. So you may want to go to globally MPLS LDP and then say under log, I want to log the neighbor, log the neighbors, and then log the adjacencies. So when an adjacency comes up, when a neighbor goes down, I want to be notified about that with a syslog message. Okay, then additionally, we need to enable logging to the console. Logging console is at debugging. Okay, so next let's enable LDP on those other interfaces. So we'll say under the global MPLS LDP process, interface gig 0000.211 and .1112, those are going to be enabled. So when we show config, we'll see that this output is similar to what we saw in ISIS, similar to what we saw in OSPF, that we define the control plane process in global config, and then under that we define what particular interfaces belong to that process. So assuming that you want to enable LDP on all of your IGP interfaces, you could pretty much just copy what you have configured under OSPF or what you have configured under ISIS. And then again, the other option is just to enable the LDP auto config, which is going to run it on all of the interfaces. Okay, end result, we can see that we have an adjacency with router 2, and then we should also have an adjacency with XR2. So as it currently stands, if we look at the show MPLS forwarding table, we should see that everything either has an explicit label number or that it says POP because we are directly connected to those particular destinations. So for example, from XR1's point of view, it is multiple hops away from router 3, and assuming that ISIS is doing the default behavior of the same cost on every interface, we should be routing to XR2 and then down to router 3. We should be routing from router 2 over to router 3. And from the MPLS forwarding table point of view, it means that we should have multiple labels for when we're doing equal cost multipathing. So just like in the case of regular IP routing, you can do load balancing between multiple interfaces running MPLS, and the router is going to do that based on the layer 3 and layer 4 information, basically the flow data, just like we would be doing it for a regular IP packet. So in certain circumstances, you'll see the router does look at the layer 3 header and the layer 4 header that's inside the payload of MPLS, but it's only using that as an input to the hashing for load balancing. It's not using that for the actual routing decision. So if I'm label switching to some destination I don't have installed in the table, I can still look at that IP information in order to say I want to load balance between the multiple interfaces. And the end result of this is that if we were to do a trace route to 3333, we should see that depending on the input to the flow information, sometimes we're going to go to router 2, sometimes we're going to go to XR2. And if we said trace route, let's source this from our loopback, or source is 11, 11, 11, 11. We'll see that depending on what the source address was, that changed the hash to the equal cost multipathing. Sometimes we're using label number 17, sometimes we're using 16,004. Now again, the way that we specifically read these labels is that they are locally significant on a hop-by-hop basis. So this means that when we forward label number 17 out towards router 2 then needs to say show MPLS forwarding table, and what is the incoming label or what is the local label for number 17. It says if someone sends me a packet labeled number 17, it's really going to 3333, but 3333 is directly connected to this neighbor who is on my local link. So this means that I'm going to remove the topmost MPLS label. I'm going to perform that penultimate hopping, or the PHP process, and then I'm going to send this as an unlabeled IP packet. So again, as we previously looked at the packet capture in the data plane, what the end result of this would be is that when XR1 forwards the packet either to router 2 or to XR2, this will have an MPLS encapsulation. But then when they forward the packet directly to router 3, this is going to have only its IP encapsulation. Now we'll see that because of this process in penultimate hopping, there are some potential problems we can get into in the MPLS core, that if our BGP peering goes to the wrong interface, or if in MPLS traffic engineering tunneling, the LDP label is removed one hop too soon, or more specifically, the transport label is removed one hop too soon, we can have traffic dropped in the MPLS core. And we'll look at some examples of that later, but ultimately we need to make sure that any devices that we're transiting over in the middle, we need to make sure that the traffic is MPLS encapsulated, because they may not know what is the final destination. Okay, so there's some questions here. Is it correct that there will be only one LDP session between two peers regardless of how many connected links they have? And what happens when the interface through which this peer was discovered goes down after the TCP session between the peers was established and there's another direct link between them, and this link is not running tag switching at all? Okay, so the question is, let's say between router 1 and XR1 that we're going to add another interface. Okay, let's say that this is going to be gig 1.10. So on router 1, we're going to have interface gig 1.10. IP address will be 10.0.0.1. Okay, and actually we need to add a encapsulation. So we'll say encap.1q10. IP address is 10.0.0.1. And we have IP router ISIS. And we have MPLS LDP, or MPLS IP. Okay, on the other end, on XR1, we'll do the same thing. So let's say we have interface gig 00.00.10. The .1q VLAN is 10. IPv4 address is 10.0.0.11/24. And then under ISIS1, we'll say this interface is running address family IPv4. And then under MPLS LDP, that interface is running LDP. Now remember from before, on XR1, I had enabled logging for new LDP adjacencies and for LDP neighbor changes. Now once I bring up these interfaces, notice that I did not get a log from LDP. But we should see that we now have an additional IGB adjacency. So if we look at the show ISIS neighbors. So I have a new ISIS neighbor between router 1 and XR1, so we have multiple neighbors between them. And if we look at the show MPLS LDP neighbors, we'll see that for the peer identifier 1111, there's only one session. However, we have multiple LDP discovery sources. Okay, that's what this message means here, that we found a new link for the neighbor, but this log message is not the same one as when you would see when there's a new neighbor adjacency. Okay, this is basically saying there was new discovery between the neighbor. There's an additional interface. Okay, if we now correlate this to the routing table, and we look at the show route IPv4, we see that now we have equal cost multipathing for 1111. However, when we look at this from an MPLS forwarding point of view, for 1111, we're going to be using the implicit null label out both of these interfaces. So we are doing equal cost multipathing between them, but it's going to be using the same label number. Now, really, to see the final result of this, we would need to be advertising some additional interfaces beyond router 1. So let's say, for example, now that we form an ISIS adjacency between router 1 and router 5, and router 5 is going to advertise its loopback to ISIS, and then router 1 is going to advertise it to XR1. So on router 5, let's say router ISIS 1, we have our network entity title. We'll say that the IS type is going to be level 2 routing. The loopback is going to be a passive interface, so passive interface loopback 0. And then on interface gig 1.15, IP router ISIS. Okay, same thing on router 1. Gig 1.15, IP router ISIS 1. Okay, if we now look at the show ISIS neighbors, we should see we have an adjacency up to router 1. And if we show IP route ISIS, we should see the routes to the rest of the topology once we perform SPF. Okay, on router 1 also I had the metric style wide. So this is the reason that, notice on router 5 we formed an adjacency. If we show ISIS neighbors, when we show ISIS database, I have the routes in the database, or at least the link state packets in the database, but they're not being installed in the routing table. Okay, this is one of the common, from a troubleshooting point of view, one of the common issues you might run into is that if the metric style does not match, they can do the route exchange, but they cannot install the routes in the table. So under router ISIS 1, I need to say metric dash style is wide. Show IP route ISIS. Okay, now we have them installed. Okay, now from XR1's point of view, let's look at how are we routing to reach router 5. If we show route IPv4 for the address 5555/32, it says I have two equal cost paths. One of them on interface gig 0000111, one of them on .10. Both of these are going to router 1. Both of them have an equal cost metric of 20. Now when we show MPLS forwarding table, we should see that for 5555, we're using the same label number out multiple interfaces. Now this is different from some of the other outputs we see here. For example, for router 3's loopback, since we're going to different neighbors, it means we're using different label numbers. But in this case, both of these routes are advertised between the same pair of devices. It means that from LDP's point of view, we don't need to form multiple adjacencies. So you can think of this as an automatic scalability technique of LDP, similarly to how BGP would work. That if we were to run an iBGP session between router 1 and XR1, we would not do a peering between 1 and the directly connected link of XR1, and then between 1 and the other directly connected link. What we would do instead is advertise our loopbacks into IGP, do a BGP peering between the loopbacks, and then based on how the next hop value recurses to the interfaces, we would need to only advertise one BGP route, but we could still be doing equal cost multipathing between the two of them. Now, the second portion of the question was, well, what happens if one of the interfaces is not running LDP? And that will be a problem if we're using this interface as part of a layer 3 VPN destination or as part of a layer 2 VPN destination. And by default, there is not a protection mechanism against this. So what I mean by this is that if we were to go to XR1, and let's say we do a trace to 5555, we should see that sometimes we're using a label out to gig1.10, or more specifically in this case 0000.10. And if we trace from the loopback, we should see sometimes we're going to the other interface, but we're using the same label number. Okay, so now let's say that there's a problem in LDP, that on interface gig1.10, we're no longer running LDP. From XR1's point of view, eventually we're going to figure this out, that router 1 stops to send hellos on that particular interface, and then ultimately the label number is going to be withdrawn from the table. Okay, we get a log message here. It says, discovery hello, the whole time expired on the interface. So it means that they're no longer a UDP neighbor on the link, but when we show MPLS LDP neighbors, this does not affect the TCP peering. The only thing that changed is the LDP discovery source is no longer having multiple interfaces. So there's only one TCP adjacency between them, but the hello packet is including multiple interfaces. And let me see, I don't know, I'm not sure if the packet capture is still running. So let me reset this. I think it's like overflowing the buffer, which is, it constantly crashes this. But if we, let me start the capture and then let's re-enable LDP on router 1's interface. So in gig1.10 MPLS IP, let's look at XR1. We should get that log message that we found a new neighbor. Okay, so there's a hello adjacency change. If we look at this from the packet capture point of view, this new hello 10.00.11, and we look at inside the specific payload of LDP, what it is going to say is that my transport address is 11, or no, this is the wrong one. I should have said coming from 10.0.0.1. Let's say the IP.source is equal to 10.0.0.1. Okay, so this hello message coming in from router 1. So it says the transport address is 1111, and that's basically it says this is just a hello message. So notice in here it's not saying what interface that I'm running the protocol on, but we see that XR1 is going to be receiving this hello from multiple interfaces. That's how it figures out that it's running, it has multiple links connected to router 1. That there's multiple hellos coming in from 1111, but we don't have multiple adjacencies to them. So if we were to filter this and let's say that we're looking at TCP traffic, the TCP adjacency is going to be going between the loopback of 1111 and 111111, not between those directly connected interfaces. And again, this is the transport source. So when both of those interfaces are up, it means that we have multiple labels. When we show MPLS forwarding table for 5555, for the forwarding, for the, do we have to say the exact route? For the label, no, not like that. Let's just say show MPLS forwarding table pipe include 5555/32. Okay, so we have two labels. We have 29 reachable out multiple interfaces. When we did the trace to this out sourcing from our directly connected link. We're going out to 10.0.0.1. When we source this from the loopback, the hash is sending us the other way. Okay, so again, this depends on the upper layer information, the layer 3, layer 4 header. How are we doing the load balancing? But then we had the case where router 1 forgets to run MPLS. So we say no MPLS IP. XR1 is going to eventually figure this out because it stops receiving hellos in from router 1. When we look at the show MPLS forwarding table, we should see that this is going to change just to one label. Okay, so on one of those interfaces, it is unlabeled. And now, depending on how we send the traffic, for traffic that is going out that physical link, we'll see that that is unlabeled traffic. Now, think about this from an L3 VPN or an L2 VPN point of view. If we are using those interfaces as transit to a remote PE, what would happen in the MPLS core is that traffic that is hashing to gig 0000.111, this would work. Okay, that one's okay. But if the interface, if the traffic hashes this way, it would be dropped because router 1 is not going to know about the final destinations. So we'll come back to this problem in more detail later, but in short, yes, this is an issue. That if you do have multiple interfaces between the devices and you're running IGP on both of them, then you also need to be running LDP on both of them. Now, there is a protection mechanism to fix this. We'll talk about this in a little bit. It's called IGP synchronization. This makes sure that if for some reason you're running IGP but you're not running LDP, the IGP process tries not to use that interface for actual forwarding of the traffic. Yeah, but otherwise, yeah, definitely good question there. Even though they have multiple links, they still only form one TCP session. There's another question, doesn't auto-config work only for interfaces in areas? No, it works for all of them. So any interfaces that are running OSPF, when you turn auto-config on, it's going to be running it. Same as for ISIS, it's going to run it in level 1 or level 2. Any link that you're running the process on, it's automatically going to enable LDP. And again, the way that you can see this, though, is with the show MPLS interfaces.